Okay, today I want to talk a little bit about projectile motion. It's a problem that I've noticed a lot of students really having trouble with. So I wanted to take a look at a couple of different ways to look at this problem, and I want to kind of break it down to the basics rather than approach it in a more complicated fashion, try to memorize a bunch of formulas. I want you to make sure to I want to make sure that you understand what projectile motion is and why we do things a certain way. And hopefully this will help you understand many different types of projectile motion problems. So let's first begin by discussing what projectile motion is. Projectile motion, in its most basic sense, is the motion of any object that is thrown or projected or hit or whatever it might be, with only one force acting on the ball or the object or whatever it might be. And when something is in the air, the only force is gravity. So from that, we should know that the only force acting on the ball is going to, again, any motion, any projectile, will be gravity, and therefore it will only be downward. So we have two different types of projectile motions that are most commonly tested in physics, in early physics courses. The first is something that is projected off the top of a ledge. And the second is something that is hit off the ground at an angle. I'm going to cover one example of both of these, but before we get to that, let's get a few very general conclusions out of this. The first is that since there's only one force acting on the ball, there's only one acceleration on the ball, and the acceleration due to gravity is negative 9.81 meters per second squared on Earth. Now, assuming most of these problems will be on Earth, you can safely use that number as your acceleration downward. The second assumption we must make is that we do not account for air resistance. Now, that's an interesting one because it would actually seem to not align with a lot of real-world scenarios. Obviously, there's air resistance in most real-world scenarios and projectiles, but the conclusion from this is since there's no air resistance and the only force acting on the object is gravity, whether we throw something horizontally or just drop it, the two objects will fall at the same time. So let me repeat that. If I have an object here, and a second object here from the same height, and I just drop this one and I throw this one horizontally, they will hit the ground at the exact same time. That doesn't seem to be accurate in real world examples because if we think about throwing something, it would seem like it would be in the air a lot longer. It actually isn't. And in most real life scenarios, because air resistance on a lot of objects is relatively minimal, you'll also find this to be the case. You can go ahead and try this. Take two pens and throw one horizontally with no initial upward or downward velocity, and then drop the other one at the same exact time, and they should hit the ground at right about the same time. Again, it's not a perfect experiment because chances are we're going to throw it with a slight upward angle or a slight downward angle. There's a little bit of air resistance, but it should be much closer than you would think. So the way we treat these problems is by using two separate motions. The motion in the x direction and the motion in the y direction. And we're going to make this the foundation of our work on this particular material. So both of these motions are just going to be essentially treated as linear motions. So we're going to consider the vertical position of the ball as it goes down. And we're going to consider the horizontal position as it moves across. So here the vertical would look something like this, and the horizontal would look something like this. Okay. And we've already established that the acceleration in the y direction is due to gravity. Okay. Now, our 5 variables of kinematics are VIY, or VI, VF, A, D. Some teachers may use S or delta X for this. That's okay. And time. The initial velocity, the final velocity, the displacement, and the time, as well as the acceleration. So the displacement in the y direction, now I put little subscripts on each of these so we could use the 2 variables non-interchangeably. In other words, the AY is not going to be the same as the AX, the VIY is not going to be the same as the VIX, etc., etc. The DY is the change in height from start to finish. It's a displacement in the y direction. The VIY is the initial vertical velocity. The VFY is the initial, final vertical velocity. The time I don't have to put a subscript on because time doesn't move in a particular x or y direction. In the x direction, we have no acceleration because there's no force acting on the object in motion. So instead, what we have are a constant Vx, meaning that if we launch this horizontally, then our Vx is going to be the same here as it is here, as it is here, as it is here. Our Vy will certainly change. Here it's 0. Here it's a little bit. Here it's a bit more as gravity pulls us down. Finally, it makes impacts with its greatest vertical velocity. Well, since we have no acceleration, we're actually only going to have 3 variables because Vi and Vf are the same. We're going to have dx and t. The dx is from here to here. It's the change in the horizontal position. And here, the dx looks something like this. Again, the change in the horizontal position. So let's try and apply this to a couple of problems. We have a cannon that is fired horizontally from the top of an 80-meter high cliff. With a muzzle velocity of 40 meters per second. The question is, how far from the base of the cliff does the cannonball land? And we're always going to begin this problem by listing off all of the variables that we know. We always know that AY is negative 9.81 meters per second squared. If you're taking this in a college course or an AP course, a lot of those courses will allow you to use negative 10 instead of negative 9.8. That's fine. It's not going to affect your answer all that much. What else do we know? Well, we know that the motion is going to look something like this. So our displacement in the y direction is from here to here. So it's a change in height, and that is negative 80. Now, it's very important to use the negative in this case, unless you were to make the downward direction positive, in which case both the AY and the DY would be positive. I don't recommend this because in certain other problems, it's going to make it a lot more difficult. What else do we know? Well, we know that the initial velocity is strictly horizontal. And we also know that it's constant, so I don't need to put Vix because it's going to be constant throughout the motion. I also know that the VIY is 0 because it's projected horizontally. At this exact instance here, the vertical velocity is 0. Well, what are we looking for? We're looking for how far from the base of the cliff will it land. That's dx. And the third variable in x is in the x direction is time, which we also don't have. Now, for the x direction, we can actually just use the basic relationship between displacement, velocity, and time, which is that Vx is dx over t. Consequently, dx is Vx times t. So one of these two, this is the same equation, just algebraically resolved. will get us what we're looking for. But in order to do this, we need one of these two variables. And if we can get the time from the y-axis, then we can actually transpose that here, since both motions, since it is one motion in effect, will take the same amount of time. So let's consider the variables we have. In the y direction, we have a, we have d, we have vi, and we're searching for t. Well, if we remember from kinematics, we have a few equations. Vf is vi plus at. Vf squared is vi squared plus 2ad. And d is vit plus 1/2 at squared. Since we're working with these four variables, we're going to use the last equation. So let's go ahead and solve this for the time. So we know that dy is -80. Now, I'm not going to put the units in here. The units are important, but for the sake of keeping the algebra simple, I'm not going to write them in here. This is 0 times t plus 1/2 -9.81 t squared. So if we simplify this, because 0 times t is just 0, we get -4.905 t squared. At this point, you can comfortably remove the negatives by multiplying both sides by -1. And then go ahead and divide both sides by 4.905. And that's going to yield us 16.3. And then since we have t squared, we're going to go ahead and square root that to get just t. And we're going to get about 4.04. So now that we know that the time is 4.04 seconds, and again, if you were to put all the units in, you would actually be able to work them out the way you would with algebraic variables. But again, I'm trying to keep the algebra simple for you here. We know that that motion is going to take 4.04 seconds. And now we have these two variables, and we can just use dx as vxt, multiply 40 times 4.04. And what we end up with here is a displacement of 116.6. Excuse me, 161.6. And there we have our answer. So this is kind of the first case of projectile motion that you're most likely to encounter. Now let's apply the same logic to the second question. We have a golfer who hits the ball on a flat course with an initial velocity of 40 meters per second at an angle of 30 degrees above the horizontal. So the ball is going to travel something like this. And the question is, how far from the tee does the ball land? So once again, we are looking for dx. So again, let's list off all of our variables. We have in the x direction, we're going to need vx, dx, and t. And in the y direction, we have viy, vfy, ay, dy, and t. Now, you'll note in the previous question, I actually did not list vfy. We can do this problem without vfy also. But I've just simply listed all of the variables here. So what do we need here? Well, we know this is always true. because once the ball's in the air, the only force acting on it is gravity. And this is where using the negatives actually becomes a bit more important. We also know that for this scenario, from here to here, this is all for part A, the displacement in the y direction is the change in height. Well, it's landed back on the ground, so the dy is 0 meters. Now, this 40 meters per second, that is actually neither Vx nor Vy. What we need to do here is actually look at a little bit of right triangle trigonometry. And if we want to take the Vx and the initial vertical velocity, we have to break this down into components. We know that this is 30 degrees, so you can either memorize the relationships between these, or you can actually build them off of trig very simply. Let's consider basic trig, the Sohcahtoa equations here. We can confidently say that the sine of 30 degrees is VIY, the opposite side, over the 40, which is the hypotenuse. Now, you can, or you may already know the equation VIY is VI times sine of theta. You certainly use that. This is just kind of a little bit more of a base level formula for that. So if I multiply both sides by 40, I get 40 sine of 30 is VIY. And that would mean that VIY is 20 meters per second. And we can use the same logic, but with cosine for Vx. Again, remember, I don't have to put Vix because velocity in the x direction is constant. So here again, I'll multiply both sides by 40. I get 40 cos 30 is Vx. You would get the exact same solutions if you were to just use the two equations. That's where these are derived from. So 40 times the cosine of 30 is 34.64. So now we know our Vx and our VIY. And we're going to once again find the time so we can transpose it over to the x direction and then solve for dx using our dx is vxt formula. So this time we have VIY, AY, dy, and t. It's actually the same exact four variables we had before, so we can go ahead and do d is equivalent to VIT plus 1/2 AT squared. So let's fill this in here. dy is 0, 20t plus 1/2 negative 4.905. Excuse me. It's negative 9.8, but if we get rid of 1/2, this is negative 0.81. I got a little bit ahead of myself there. So half of negative 9.81 is negative 4.905. And now what we have is a pretty basic quadratic equation. What we can do is factor out the t. We're left with that. And then take both of these factors and see what values of t make those equal to 0. So the first answer you get here is t equals 0. And if you think about what you're solving for the time when the change in y, the dy, is 0. Well, that makes sense, because at this point, initially, before we've moved the object, the displacement vertical is 0. So we're not really interested in this solution. We're interested in this solution. I'm going to move the 4.905t to the other side and divide by 4.905. And we're going to get a time of 4.077 seconds. And then after that, this is pretty straightforward. We now know the time. We've transposed it to both the x and the y. I would say, okay, now dx is just the vxt. So dx is going to be 34.64 Vx, and then the t is 4.077. And our dx is going to be 141.2 meters. So that is our solution to part A. Now for part B, I'm going to go ahead and change the color here. The question is, what is the maximum height the ball will attain during its flight? Now, we have two ways of doing this. One that will only work in symmetrical motions, and the other that will work all the time. This motion is symmetrical. We started on the ground, we're going to finish on the ground. So we can actually split this motion into two. And if we split the motion into two, then we can do something with the time. We can take half of the time. So it's 4.077 divided by 2, which is 2.0385. And the reason that this works is because it's going to take half the time to travel from here to here, and another half the time to travel from here to here. Well, I'm interested in the position of this ball at the half time. So now, well, let's consider just the y values, because I'm not really all that interested in the x value from here. I want to know the max height. So I'm looking for dy when time is equal to 2.0385 seconds. We know that the VIY is not going to change. We're still using the same motion, so it's still being kicked off or hit at the same exact rate, still the same motion. And we certainly know that the AY is not going to change. That's the gravitational acceleration. So we know the time, we know the A, we know the VI, and we are looking for the D. So again, we can use dy VIYT plus 1/2 AYT squared. So dy is going to be VI, which is 20, times the time, which is the half time, right? We're not interested in what happens in the full time. We already know it's going to be on the ground at that time. Plus 1/2 negative 9.81 2.0385 squared. Now we can actually go ahead and put these values right into the calculator. Now what we're going to get here is 40.77 minus 20.38, and that's going to get us 20.39 meters. Now there's a second way to do this, and this will be more applicable to non-symmetric problems. So I'm going to cover this in a second video because, like I said, I wanted to keep this one pretty basic. But there is a second way to get the max height that will actually be more applicable to more problems. But we've already gone on almost 25 minutes here, so I'm going to save this one for a second video. If you want to see that solution, I'll have it up within a day or so. It's on our YouTube channel. If you found this helpful, guys, please subscribe. We have other videos up, things ranging from SAT, ACT, algebra, and calculus. And if you want us to do a video on a particular topic, please don't hesitate to contact us. Our contact information is right below in the description, or you can contact us directly through the YouTube channel. I hope you found this helpful, and thank you for watching, and best of luck.